Hello, everyone. Thank you for coming to today's colloquium presented by Zoe and Noam from UTAT. They'll be telling us today a bit about some of their work on their satellite and how it can be used for imaging agricultural problems and other applications. And I think at the end, they'll be running a bit of a workshop to see, so you can see how you can get involved in their work as well. Usually we have snacks to start, but since we're in the computer lab, we can't have snacks in here. So stay till the end for free food.
All right. So our mission is called Finch. It's a hyperspectral imaging satellite. We're going to get into what this means in a little bit. But we're basically going to be explaining a bit about our methodologies and objectives and basically what we do in our day-to-day. I'm Zoe. This is Noam. And let us know if you have any questions.
Yeah. I'm Noam. I've been part of UTAT in some capacity or the other since 2022 and part of science for a little over a year now. And I've worked on quite a few of the different components of the satellite. And most recently, I've been focusing on leading the atmospheric modeling subteam.
Yeah. So I'm Zoe. I have been a part of UTAT since December 2024, January 2025. And I'm in the spectral unmixing part of things, which we'll get into a little bit what this means. Yeah.
Now, as you've heard, we're not presenting work that only the two of us have done. This is a multi-year long project involving many, many people. And we are presenting what the science team has done. Yeah.
Okay, so UTAT is a student-led design team. We have 4 divisions, and they each design different things. Ours is centered around designing satellites. We already have a satellite up there. It's called Huron, and it was just for communications. You can see the patch here, and we're currently working on Finch. So what Finch is going to do is it's going to estimate crop residue at an individual farm level. It's a very cheap satellite, and it's hyperspectral, which means that it images at various wavelengths. You can see, you will get a little bit into that later on. But what we basically do is we leverage many engineering constraints, and we image outside of traditional wavelengths, which makes our data analysis much more complicated, but also much more interesting. And we're actively doing research into new algorithms and models that will allow us to estimate crop residue in these like awkward wavelengths.
Okay. So UTAT itself is divided into 4 parts. We at Space Systems design and build small satellites. Rocketry designs and builds small rockets for competitions and various other such programs. And UAS does much the same, however, though with unmanned aerial vehicles. And aerospace policy and law largely focuses on the more theoretical aspect of what the legal implications of aerospace work are. We are a very small group, and we are a close-knit group, relatively small for we are effectively an aerospace company. And we build satellites in our spare time. Now, for 4 members, there are varying levels of commitment, and generally, while we do want people to come in every week, that is not always possible. So our UTAT relies on people who both come in every week and who come in occasionally to do a bit of work. We are mostly professional, and we mostly adhere to safety standards. Although if anyone stops by our lab, make sure don't eat anything in there and wash your hands after. Well, that lab is in my hall. We built everything there, and it is really quite small for what we do. We present at conferences. More recently, science presented at the Canadian Symposium on Remote Sensing, and optics and various other groups presented at the Small Satellite Conference. And I said that we are an aerospace company, but we are not paid. It would be very nice if we were, but we are not. We analyze quite a lot of data to retrieve how much crop residue is left on the field. In the field of remote sensing, crop residues or dead plants are referred to as NPV, and we will be using that acronym throughout the slideshow, non-photosynthetic vegetation. We use machine learning to implement and design various models. We need to do quite a good deal of atmospheric modeling so that the data we have is usable, and we, alongside this, we perform more specifically, we perform atmospheric effects inversion on top of atmospheric data, which is what we hope to receive from Finch. And the team itself is, the team and the work especially is extremely interdisciplinary. We have people from physics, we have people from engineering, and we have both physics and engineering issues. We conduct ground truth applications, ground truth operations, and are currently working with the NMAP satellite, Emily Innovation Farms, which is our imaging site, and Agriculture and Agri-Food Canada. We build pipelines to do data analysis, and we also validate the design decisions of other teams with in mind the scientific mission.
Okay, so basically what makes Finch different from all the other alternatives out there is the price tag. So it is much, much cheaper than what is on the market there. And the idea is to use that to be able to give this information to individual farms, right? Because an individual farm won't be able to pay for a super expensive satellite, but we still want to be able to provide them with the information that is the relative abundance of crop residue / non-photosynthetic vegetation, which basically just means dead plants. And the reason we want to measure this is because it's very important for sustainable agriculture for various reasons. First of all, if you have more crop residue, then it helps retain soil moisture. It also prevents soil erosion, and more importantly, it also serves as a measure for tillage intensity. So for those who are unfamiliar with tillage, it's like basically after harvest when they go and like move the earth around to help it integrate it better. But if you do it too much, it's also bad. So this measure is really important for farms that want to be more sustainable, and they really need this metric that we hope to be able to provide at a low cost, right? But obviously with this low cost come a lot of challenges, and it's basically that we cannot image in the traditional wavelengths for various reasons. First of all, the sensors are really, really expensive, and they also need to be cooled very aggressively. And they are very, very big, and our satellite is small because obviously launching big stuff into space is really expensive. And it also needs a lot of power. So within all, it basically means, cheap satellite, just because it's inexpensive, but also because it introduces a bunch of new challenges for us and specifically for science as to what we're gonna do with this data, right? So you can see here in this graph, this is our sensor efficiency curve, and each color represents one of the different things that we're going to measure. We actually want to obtain crop residue, but we also measure soil and green vegetation to obtain it. Yes? Well, that's kind of the whole thing. We don't deal with, it's a regression, right? So we want to estimate abundance. So the output of a whole pipeline is a number, not a yes or no. And I'm going to go into how we exactly measure this in the next few slides, but that's basically like what everything we do is about. Yeah, it's like kind of how to measure that.
I should mention, the lignin cellulose absorption band is here. Yeah. Our spectral range ends here. We are simply not able to image the lignin cellulose absorption band, which is the industry standard for on photosynthetic vegetation.
Yeah, that's what makes our job hard.
So what do we want to do? We want to estimate crop residue from hyperspectral images. We use data that is either similar or that we try to get to be similar to the data that will come from Finch, to ensure that our models and our methods are accurate to Finch's capabilities, and also to the atmospheric effects within our imaging, within our spectral resolution. We use machine learning to develop algorithms to aid with modeling and unmixing. We create and apply atmospheric and surface models to the data itself, and we unmix the spectra received from satellites and from the ground to estimate the abundance of non-photosynthetic vegetation.
So I'm gonna go a bit more into the unmixing side. So we basically have a data set with labeled data. We use part of that data set to train our model. That can be either traditional statistical models or more machine learning-ish models. And we then, using these models, predict the values for the unseen label and then evaluate the outputs. So it's generally as to provide the learning regression problem, right? So we have various methods, just a few examples. For statistical models, we use both Bayesian and frequentist approaches, and we use them to fit to different functions. And for machine learning models, again, we have a bunch of different types. Right now, I think the one we use the most is ensemble decision tree learning, but we are constantly trying new methods. Yeah. So basically, our input is the reflectance, and we have reflectance from 900 to 1700 nanometers, and a data point every 10 nanometers, so 910, 920, etc. And our Y is the abundances, so we have the abundance of non-photosynthetic vegetation, green vegetation, and soil, which we can predict together or separately too. And just to get a bit of an intuition as to how we quantify success, we basically do this by plotting the true abundance versus the predicted abundance and then taking R squared of Y equals X. So intuitively, Y equals X is our target because that means that for the true abundance of, say, 0.2, you're predicting 0.2, right? For target abundance of 0.5, you're predicting 0.5, and so on and so forth. So we basically want to get as close as possible to this line, and here you can see an example of this graph. So you can see that for some values, it's okay, and then some others are really out there, which is not good. Yes? Sorry? A little bit, yes. So this is obviously has nothing to do with, or well, I guess it does have a little bit, but this is not the actual data. This is our predictions on the data. But it's true that if we see on this graph a certain trend, or we see a certain function in it, then we can just apply that function after we apply the first method, right? So you basically can have a function of a function and just like kind of build it from there. So yeah, that's something, definitely something we look at as well, and something we can that is done regularly too.
Okay, so in order to actually perform unmixing successfully, we need extremely accurate atmospheric and ground models. And there are a number of issues standing in our way. We have, returning to this graph, within the Finch spectral range, there are significant atmospheric absorption bands. These are useless. And even in the bands that still have that are still able to be transferred through the atmosphere, there are quite significant atmospheric effects that have to be accounted for. We have to account, like as any other remote sensing satellite mission, with a cloud cover, both directly blocking the site and causing reflecting light from the sun themselves, drowning out the data. Aerosols in the atmosphere that are not expected in standard models, and also the day-to-day light conditions. We also take into account soil albedo, plant decomposition, and the relative water content of the vegetation on a day-to-day basis, because each of these significantly alters both alters the spectrum of the end members in a manner that would, if unaccounted for, would cause unmixing to return rather incorrect results. So how do we deal with this? We use data from both the top and bottom of the atmosphere, and also from pure end members in labs to validate our models. And many of our models are, in fact, industry standard. One of the ones we use extensively is MODTRAN, developed and used in part by the US Navy, and the industry standard for atmospheric radiative transfer. We also, in many cases, develop models and pipelines for this application, and these are each strenuously tested and, in many cases, trained for their accuracy.
Okay,
Thank
so
you.
Yeah, we'd like to have a little Q&A now. So if anyone has any questions about the content or also the team and its structure. Yeah.
It varies from person to person. I have been coming in practically every Saturday for the past 3 years, and spending anywhere from 1 to 5 hours at my home working on UTAT. Other people come in once every 3 weeks. Other people are entirely online. Our current science team science lead will be spending the vast majority of the term entirely online. And many others, in the end, it just is whatever you are willing to.
I think what the previous lead first said to me when you come in is you get out of it what you put into it too. So obviously, like the more you put into it, the more you learn. But we obviously understand that people who come in have a bunch of responsibilities, including school and other stuff as well. So it's really how much you're willing to give.
Our precise budget information is protected by an NDA, and I don't even know it ourselves, but one of our goals is that the satellite is sub 500,000, which for the aerospace industry is extremely inexpensive.
Including lunch.
Including lunch. You. The short answer is we've been getting, up until last year, a levy through the University of Toronto Student Union. That's about $2 per term per student. Now that is no longer the case because we lost the levy, and we also get sponsorships from various other groups. But again, we don't get paid, so that makes it much, much cheaper. Yeah, in many ways, yes.
Our systems engineers, our project managers, and a very like corporate structure, if that makes sense. So we have clear like so space systems is like 150 people, and UTED as a whole, I'd say 250.
A bit more.
more. Yeah, 300 maybe. Any other questions?
Yes. Oh, well, all of what we do is extremely specialized. Nobody has the qualifications for this.
Yeah.
We
Yeah, you learn on the job. Like I knew absolutely nothing. I wrote my first line of code at UTEL. Like I came in knowing absolutely nothing. You learn on the job. It's such an interdisciplinary and specific field that no one is ever going to know enough until you join and actually start engaging with the project. It's part of the learning curve.
we're so specialized that even professionals who do this need to learn on the job, because what I'm doing, for example, there is one advanced graduate seminar at the entire university that does the basic portion of it from a very wide perspective. So it's you learn on the job, and anything you already have is extremely useful. Well, we don't. UTAD rocketry does not have space launch capability for CubeSats.
I don't think Canada has.
No, it doesn't.
Yeah.
It's not even optimal for. Yeah.
Yeah.
Canada's geography isn't even optimal for space launch of CubeSats. It's random, but we we outsource with the launch provider. For example, Heron was. Yeah, correct.
Yeah.
Heron was launched on a Falcon 9 from Vandenberg Space Force Base.
Yeah. It has like
Here's,
a little red circle.
Yeah, here's our satellite inside of a box owned by the launch provider inside of the fairing of a Falcon 9. I don't remember.
NDA protected.
No, I don't think so.
It wasn't for her?
For this bit?
For Finch, it's NDA protected.
For the launch or for Finch?
Oh.
I'm not sure exactly, but if you want, on the SpaceX website, you could look at the rideshare, input various details about the satellite, size, mass, orbit type, and then it will give you a cost estimate. Well, first of all, we are a 3U CubeSat, so we operate within that. We use that structure, and we don't close our eyes to what is already there. We use quite a lot of what has already been done to advance on with our design, but it needs to be a ground-up design. We do this. The layout of the satellite is intuitive, so it is common with a few other remote sensing CubeSats because it is you generally want to have a camera in a certain place and a computer in a certain place and solar panels in another place. But our specific design is entirely unique. Phase C, so detailed design. Sorry? What's that? Detailed design. Precisely that. We designed the satellite in detail. We have already worked out what we want to do, what the general design is, and so we need to write all the code. We need to test all the prototypes. We need to figure out all the prototypes. We need to For us, we need to work out unmixing so that the scientific mission is capable. It depends on the exact subsystem. For us, for example, we don't have very much to do after phase C, but other teams do.
Any other questions?
How long is exposure time? I'm trying to remember the number that we have. Not long.
No.
Yeah. I don't think it's precisely determined. Approximate range.
Yeah, we have an approximate range, but because the optical setup is not set yet.
Yeah, that's optics, not science. So I'd have to go digging through documentation.
Yeah.
Sorry. Oh. Talk to Ilya. And good luck.
Okay.
Let's move on to the
We prepared like a little workshop. The links are in the Slack. If you look at the sorry, not in the Slack, in Discord, in the announcement. Yeah.
So there are two options for you to choose from. You could either do a atmospheric modeling workshop or an unmixing workshop.
Yeah.
Unmixing.
Yeah. So like the abundance estimation. So for the unmixing one, you just basically you'll see that there's a function that hasn't been defined yet. Then it's the one that you actually train and then predict on. You can use linear regression from scikit-learn, or you can come up with that or your own methods and just like test it out right there. Yeah, try to get as good as a prediction as possible.
For the atmospheric modeling, you're given a basic radiative transfer model based on a Lambertian reflectance, and you have to code that as a function, and while making assumptions for determining various numbers that have not been provided, and also working out functions for the atmospheric absorption, and then that will be applied to a spectrum, to one of our actual and non-photosynthetic vegetation training spectra.
If anyone has any questions, let me know. If you want to use the linear regression one, you can check out the documentation for it on the scikit-learn website too. It's very nice. It has nice examples. Yeah, let me know if you have any questions. I'll just be going around, I guess.
Might as well.
Yeah. Bye. Thank you for your